Okay, so over to you, comrade.
Okay, cool. So can everyone see my screen and my maths notes?
Yeah.
Yep, cool. Okay, so we are doing A-level maths again. I'm pretty sure I filled in this exact session last month as well, so hopefully this should go fairly smoothly. Now, I have Grace, Kanako, and Niels here right now, correct?
Yeah.
I don't think I had most of you guys last time I did this, so yeah, let's bear that in mind. Okay, so we have a few topics to go through. We're going through sort of algebra, then some functions, and then some differentiation and integration in the second hour, and we'll probably take a bit of a break in the middle. So, yeah. The first thing that they want you to look at is the modulus function by here, right? In the notes, you've got a nice little list of things that tell you lots of information about the modulus function. Last time I did this, I figured the more important thing to talk about, provided that you understand what the modulus function means, which is, generally speaking, that's fairly simple, right? It just makes everything positive. Most of the properties make a lot of sense. What's more useful to talk about is the actual types of questions that you get with it, right? So you're relatively commonly get in papers. Let me just grab a pen. You'll relatively commonly get in papers things that are doing, 3 mod x minus 1 equals 2 mod x. Right? Something like that. And they suggest a variety of ways of solving these. Actually, so that one is, yeah. Okay, so there are 2 points here that are worth bringing out. There's this line here. I don't know why it doesn't let me draw short lines. There's this line here, and there's this line here, right? This one is one common way of looking at stuff, right? And this works off the idea of okay, I mean, yeah, this equation is actually trivial to solve, but yeah. So this line works off the idea of one of the easiest ways to solve modulus equations is just to square them, right? Because as soon as you square a modulus number, squaring a plus or a minus number gives you the same answer, and so it essentially makes no difference at that point, right? The other one that is worth talking about is this idea here, and this is a little bit more telling, right? So here we have square root of x squared is equal to mod x, right? Now, what do we know about square roots of things? So, for instance, what's the square root of 9?
3.
Or?
-3.
Yeah. So that's the key idea there, right? So modulus, I suspect, I have no idea, but I suspect it probably showed up about the same time that people started figuring out how square roots worked and all of that business. But yeah, so that's the core point, is that actually your square root and your modulus are intrinsically related in that way, right? That's where the whole idea of squaring things to go back to normal comes from. So what did those equations look? I don't know. So this equation, for instance, right? this one is actually very simple to solve if you take a look at it for a moment, right? What are the answers to this one?
Is it 3x minus 1 equal 2x and then x equal 1?
Okay, so one important rule to note. Whenever you get modulus signs in an equation,
Yeah.
you are always going to get two answers. And that again comes back to this idea, right? What else gives you two answers all the time? Well, quadratic equations, right? With an x squared in. So in the same way that if you've got an x squared, you're going to get two answers. If you have a modulus sign in your equation, you are going to get two possible answers.
Okay.
So in this case, there is a very simple way of solving this, right? Lots of people, so the other thing to be aware of is you can do anything to modulus signs that you would do to anything else, right? So we can easily rearrange this into modulus of x equals 1, right? Subtract the 2 mod x off both sides and move the 1 across. What answers does this give? So what is x? Am I still here? Can you still hear me?
I can just start hearing you now.
Ah, right. That's interesting. Okay. Well, hopefully, okay. Tell me if you can't hear me again for a bit. But yeah, okay. So where did I leave off? What was I saying?
You left off practically when you had just finished making it modulus of x equals 1 for me.
Yeah. Okay. So are the other two, can you hear me as well?
What?
Can you both hear me? Can you both hear me fine?
We can hear you, but there was one instance where you dropped out.
Yeah, okay, cool. All right, so you can do to the equation anything that you would do to any other algebraic component, right? So in this case, you can rearrange this quite trivially. So what are the answers that you're going to get from this?
Plus and minus 1.
Yeah. So I don't think that they tend to do very much that's particularly complicated with modulus signs. At best, try and solve it by just doing things like this. Failing that, square them. But if you can just rearrange it into mod x equals something and then put the plus and minus in, that's the kind of ideal situation to be in. The other thing to note, the other technique that you can use, which I think is sometimes quite nice, and I think I've talked to some of you about it before. I definitely mentioned it last time I went over this. Whenever you've got two modulus signs in an equation, you have two possibilities, right? And uniquely two. Either your two modulus signs can have the same sign, or they can have different signs, right?
Mm-hmm.
But so there are four possible combinations in total, right? This one can be plus and minus, this one can be plus and minus.
Mm-hmm.
So that's a total of four combinations. But two of those pairs are actually just the same equation made negative. So the other thing that you can do when dealing with an equation like this, obviously we've got a very simple example here, is decompose it into your two possibilities, right? So you can have 3x minus 1 equals 2x. So here they've both got the same sign, or you can have 3x minus 1 equals minus to x. And here they've got different signs to each other. And those are the two unique combinations here. So, yeah. Of course. Yeah. Don't know if that actually seems a little odd in this case, but fair enough. What do they usually do? I forget. They often like, to be fair, more commonly they like putting a lot of the time they deal with very simple mod equations and they tend to put exponentials in there. So we will get back to that later on. That's one of their favorite things to do. Okay, so right, I've talked long enough about that and I've babbled on. So let's move on. Polynomials and the factor theorem. This is one that is definitely more worth talking about. Technically, in your syllabus, you are supposed to be able to go up to quartic equations, right? Which is something with an x to the power 4 in. Practically speaking, in an exam, you will usually be dealing with cubic equations. So going up to x to the power 3, right? You've got two theorems here that they like you to use. It is worth pointing out that the factor theorem is essentially just a subset of the remainder theorem, right? It is also equally worth pointing out that you don't really need to know the remainder theorem particularly much. I don't think they ever ask about it, ever, because it's not really very useful in most realistic contexts, apart from probably some weird pure math stuff people do in fourth year at university. So yeah, the key thing to remember about this is this rule here, right? So that's saying if x minus t is a factor of the function, then p of t equals 0. More commonly, you use this the other way around, right? You're saying if I have a function, if f of t is equal to 0, then I know that x minus t is a factor. And that is the form that you tend to use it in, right? Okay. Let me stop a minute here. Question, because I want to make sure that you guys are actually getting something useful out of all of this. So, because you guys have all covered a relatively, you guys have all covered this for a relatively long while now. So are you, basically, can you tell me if you're very comfortable or not comfortable with a topic so that I know whether I need to be spending a lot of time on it? Because I feel like if I'm just sitting here and explaining the basics to you once a month, then that's not of any real use to you guys. So how are you guys on the whole factor theorem and factors of polynomials side of things?
I'm good.
Niels?
I think I'm okay too.
So do I. I think I'm pretty good on this.
Okay, so in that case, shall we just move on from this to other bits and pieces?
Yeah.
Yep. Okay, cool. All right, so if we move on then, so we have this kind of by and large algebra topic. So we have 10 minutes left to spend on it. So we've got binomial series and we have partial fractions. So are there any of you three that would particularly like to focus on one or the other of those, or equally any of you three that think one or the other of those is really not very useful to you to go over?
I'm pretty good with partial fractions.
I think I would like to go over partial fractions. I haven't really been looking at that particularly much, so I'm not sure how good I am with that. binomial series, I should be quite okay with that.
Okay, right. We'll talk about them both a little bit then. Okay, so binomial series, they've got
Hello?
yeah, okay. So binomial series, okay, hang on. Can you guys hear me at the moment?
Yeah.
Yeah, okay, cool. So binomial series, they've got they've written it out in not the nicest formula, but it'll do. So there is a pattern to your expansion, right? There are 2 points to make about binomial series. The first one that is just worth being aware of is you can make your life a lot simpler if you remember just the first couple of coefficient sets kind of independently, right, on their own without the formula. So do you guys know what I'm talking about here? So the idea of you've got your 1, 1, 1, 2, 1, 1, 3, 3, 1, 1,
Yeah.
4, 6, 4, 1. Those are probably the ones that are most worth remembering, right? Just because if you are expanding a double bracket to the second, third, or fourth power, you can do it a lot quicker with this than because all these are just these n over 1 or this thing here compacted down when you put in a certain value of n. Obviously, if you don't work it out directly, then that makes your life a little bit quicker. Yeah. Yes, and then the other thing that is worth talking about is this bit, right? So the idea of taking everything apart from 1, right? There is also a point to be made about what would you do if you had something like x plus x squared. Okay, that's not the ideal example, but something like this to the power of n. How could you turn this into a binomial with a 1 at the front?
You need to take x out of the brackets.
Yeah, so that's why I said it's not an ideal answer in this case. However, in general, so in this particular case, yeah, that works and that's fine, which is what. But in general, there is one very simple rule which is useful in a surprisingly large number of cases in maths as you get further on, and that is the fact that 1 minus 1 is 0. Or indeed that anything minus itself is 0. And therefore you can always stick that in wherever you like. And so in any given case, if you've got some stuff in that doesn't have a convenient 1, you can literally just put 1 minus 1 in, and then the minus 1 is going to become part of your, x by here. And the 1 is the one at the front. Right, so this gives you your 1 if you're ever short of it, and that's a useful thing to do. So in this case, you can have 1 plus x squared. Why is it looking so like spiky all of a sudden? The writing, I don't understand. 1 plus x squared. Plus
Oh, that's why your zeros are.
Yeah, it's like a weird hexagon. I don't understand why. Everything's just gone really spiky on this. Yeah, I didn't carefully draw out the hexagon. That was that was a very odd coincidence when I saw that. But yeah, so yeah, this is actually worth remembering in general. There are quite a few different cases where it can be surprisingly useful. Another one is things like partial fractions.
Sorry, in that last one, your whole x term, so in terms of like the formula being 1 plus x to the power of n, your whole x term is that x squared plus x minus 1.
Yes.
Okay.
Yeah. So that's your x term there. You won't usually need to use this in this particular case, but it can be very useful in the case of partial fractions, or not exactly partial fractions, but in the case of integrating funny fractions later on. And yes, we will see that right towards the end of today, actually. Okay, right. Let's talk about partial fractions just a bit briefly then. So, what have they? Okay, so the notes have it in a very nice general form, but it is also a little bit obtuse and obscure. So, the key idea with partial fractions is that what? Okay, so the important thing to make sure that it's always solvable is you need to have a higher power of x on the bottom of the fraction. Okay? So you'll notice here that up the top it goes up to x, but down the bottom you've got x times x, so that goes up to x squared. And similarly here, this goes up to x squared, but this in total will go up to x cubed. So that's what you require to be able to do partial fractions. The key idea, pardon?
Why is that so?
So the reason is that ultimately what you are turning it into is these things, right? You're turning it into some number over a fraction, right? And because, so obviously that has a bigger power of x on the bottom than the top. So to make that unique, to make that always reachable, you need to start with a bigger power of x on the bottom than the top. So yeah, if you don't, you can still split it up if you want to, but you will actually get x's on the top as well as the bottom in that case, like here. So yeah. All right. The key idea, however, looking at what we actually do with partial fractions, is that we have a fraction with some possible brackets on the bottom, right? If you don't have brackets on the bottom, then the first thing that you need to do is factorize before you do anything else, and that is most commonly comes up. Someone has their mic has me coming out quite loudly in whatever room, and I'm getting a lot of feedback. So yeah, whoever's not got headphones on, can you either put headphones on or turn me down a bit? Okay, yeah, that's fine. A little bit anyway. Okay, so yes, if you come across something where you want to do partial fractions and you don't have brackets on the bottom, first thing to do is factorize. After that, the idea is you put it into this form, right? You just put all of the different factors as bottoms of the fractions. And the kind of, not really exception, the addendum to that rule is that if you have a squared factor, so for instance, if you've got x plus 1 squared as one of your factors on the bottom, then you put in as possible fractions both the factor on its own and the factor squared.
Why is it that we actually do that?
In all honesty, I don't actually know. Yeah. So okay, yeah. So it comes down to the fact that technically you've got it comes down to the fact that you've got your constant, right? Or rather that in general, you can separate it off into a fraction that has this squared in it, because that's independent. In general, okay, yeah, basically, the best way to look at it, and the way I've always looked at it, is that I assume someone knows why, and I just run with it. Yeah, that's basically it, to be honest. Sorry, not much more to say there. I think it comes fundamentally from the idea that if you separate the fraction out, then in theory, what you could do is have A plus B plus C over the same fraction. So you can have two different numbers over the same fraction. And then in that case, to differentiate them out, one of them has to have an X in it. You come across this. Oh no, you come across that when you do second order differentials. I think that's it. Yeah, that's further maths. Yeah, so you come across this idea briefly in further maths. But essentially, basically the other form that you can put this in is B over your bracket plus CX over your bracket. So this and this are essentially equivalent ideas. It's about having multiples of this bracket while also making them different things. And this is just a nicer one because it maintains just having a number on top and not an X. So that's why they do it here. Yes, okay, that makes sense actually, yeah, fair enough. Yeah, so it's about having different, having three possible things, because you've got three factors on the bottom, so you're always going to need three fractions. And these have the same factors. But yeah, I would argue that the best way to think about this is actually just putting the fraction back together, right? Which sounds like an odd thing to do. But the best way to think about this is to go back to how you would add up the fractions, right? Which is multiply through by the denominators. So in the top case, you would get A times the second bracket plus B times the first on top, right? And then what you do after that is you're just solving the top equation for A and B. And usually the easiest way to do that is to solve it by setting your brackets, your factors, to 0. By trying out certain values of X. Okay, we don't really have time to go into a particularly detailed example of that here, of the whole sort of setting X to certain values to find A and B and C easily. But if you don't know how to do that, then practice it or ask someone while you're doing one of your papers or something like that, because that is definitely a useful thing to get used to doing. That's what they're talking about here when they suggest substitute any constant. It can be any constant. There's usually certain ones that make your life a lot simpler. All right. Okay, yeah, let's move on from there. Okay, so the next half an hour, we are due to be talking about logs and exponentials and then trigonometric functions. Usually, I find that people, despite the fact that it's got almost no space dedicated to it in the notes, I find that people want or need to spend more time on logs than they do on the trigonometry side of things. Would that be the case here for you guys? Hello?
I'm okay with what we did last time, so I think it's up to the others.
Niels and Kaneko?
I'm okay with trigonometry, but I'm not sure about the logarithm because I did some of the questions and I didn't get right answer.
Okay. Niels, how about you?
I should be okay with trigonometry as well. Logarithms, I might be a bit foggy on still though.
Right. Sounds like experience is holding true in this particular case then. All right, so we will focus on getting logarithms down, and then we will talk through trig briefly at the end. Yeah. Okay, so actually, I'll briefly mention trigonometry. I'm assuming that you're given the identities in your data booklet. If you are, then that's great. If you aren't, basically the trigonometry at A2 ultimately boils down to, do you know the identities? If you know the identities, everything is fine, or if you're given them, everything is fine and you know how to use them. And otherwise, you just need to learn them. Hence why people tend to be more okay with it. Logarithms, in theory, should be the same idea, right? So, yeah, there are 2 points to make. First is this one up here, right? And so I think you asked this question last time, Grace, which was, what actually is the log function? And I said that I would argue the best way to think about the log function is asking a question, right? And that question is, I'm saying, if I say a to the power of what is y, I'm asking, what power do I need to raise a to get y? So if I ask you, what power do I need to raise 3 to get 27? Niels, what is the answer to that?
Wait, sorry, say that again.
If I ask you, what power do I need to raise 3 to get 27?
You need to raise it to 3. No.
Yeah.
Yeah.
Just cube it.
Yeah.
And that's what we're doing here, right? We're saying, what power do I need to raise 3 to get 27? And in this case, that's a nice whole number, right? So what the log function is essentially is it's an extension of that question to numbers where the answer is not a nice whole number that we can just answer off the top of our head or by doing some figuring out, right? So that's essentially what the idea here is. It is definitely worth being comfortable with this explanation. Do any of you know, you've done enough past papers by now that you would know if you did, do you need to know how to derive the log rules?
No.
Sorry, is that a yes or a no?
No. Well, I've never come across anything where you...
Right, okay, that's convenient, because that probably takes longer to get your way through and to remember than the rest of it. That's nice. Okay, so beyond that, we have a whole set of log rules here, right? I would point out, and I have previously, that they are in essence all the same rule, right? Apart from these two. These two are a bit weird. We will come back to them. These ones are the ones that you will use most commonly by a long way, right? First one is that n log of a equals log of a to the n, and vice versa. The second one is our log a plus log b equals log of ab. And I'm just going to write it like that for now. Now, we've got these written much nicer by here. The reason that they have written log to the base a for all of these, do you know why that is?
As opposed to what?
Yeah, okay, so better question might be to start off with. Do any of you know what log to the base A means? No. Excellent. Okay, so
Isn't it just like a number that you can put in later?
yeah, but more to the point, these rules are all done in log to the base A to make the point that they are true for any log to the base of anything. Okay? So the base of a log, A in this case, or 3 over here, is that part of the question. That's what we are raising to some power, right? So if we have log to the base 3, we're doing 3 to the power of something. If we have log to the base 10, we're doing 10 to the power of something. If we have log to the base e, which we call ln, then we're doing e to the power of something, e to the x, right? That's what our base is. So log to the base a, I don't know, I think they just use it because it's the first letter in the alphabet, to be honest, but it's kind of convenient because you can think of it as a for anything, right? It is a because it works for any number, for any log. And that's the important thing about all of these. Okay? If you see log written without a base, then log on its own usually means log to the base 10, and ln means log to the base e. Okay? Those are a couple of points to remember. But yeah. It is worth pointing out that I think it's nice to remember that these two rules are essentially the same thing, right? Because if you make a and b both a, right, log of a to the n is log of a times a times a times a times a n times, right? And so if you then separate that out into pluses using this rule, that's log of a plus log of a plus log of a plus log of a n times. And you know that if you add n of something together, you've got n times that. That's just what multiplication means. So these are actually just the same rule. And in the same way, if you combine them, log of b over c is just the same as log of b times c, except now you've got c to the minus 1. And c to the minus 1 is minus log of c, or log of c to the minus 1. So they do all link in together quite nicely. Now, the other two to point out are these two. These are rules for converting between the bases of logs. And again, I don't think that in your syllabus or rather in your exams, you ever use this much. Would I be right in thinking that?
I haven't seen yet.
Yeah, I've gone through a fair number of A2 papers with people now, and I've not come across it. So I think it's not desperately worth talking about. Aside from the point of, I think they've kind of missed a trick here, but at the same time, it kind of makes sense. So this point here, they've done log to the base a of b is log of b over log of a, right? The reason that they have done this is because sometimes, log to the base of a funny number is not always easy to find. These days it tends to be because you just put it into your calculator, and most calculators will take logs to the base of strange numbers. If you don't know how to do that, it is worth checking and making sure you do. In this case, these two logs, you will notice they've lost the base a, right? You could assume that these are both logs to the base 10, but in fact, they could be logs to the base of any number, including a for that matter. But yeah, so other thing to point out, can anyone tell me what is log to the base a of a?
1.
Yeah, why?
Because it says up there.
Oh yeah, fuck. Shouldn't have said that. Damn. Never mind. Okay, I'm forgetting that. More to the point, why beyond? Because it says up there.
Because
Well,
no. No, Zika.
so anything, if you have the same number to the basis of it, it will become 1. It's like taking, well, 10 to the base of 10. What do you need? 10 to what power is 10? 10 to power of 1 is 10.
Yeah, excellent. Good. Yeah, I think that more than anything is one of the best ways. Like, if you understand why this is like logically true and it seems simple to you, then that's a good indicator. I generally find that you understand logs fairly well. Yeah. Other point to make, and as demonstrated by this graph, why can we not take the log of a negative number?
Because
Can't have something to the power of something can't give you a negative number.
Yeah. So you can't take 3 to some power and get -9. That just doesn't work, right? So that's why our log is only in the positive chunk of the map. Okay. Kaneko, in particular, you said that you had been having some trouble with logs in some of the questions you've been doing.
Yeah.
I'm assuming that in the general sort of run over that we've done, maybe we've cleared something up, but if we haven't, what would you like to go over in a little more depth?
I just like something confused when the not logged. If the question say like ln,
Yeah.
and then if say the e the power of -2x or something, and then find the x.
Yeah. Okay. So that's definitely worth talking about. Okay. So that's cleared off enough. Ln of x is just log to the base e of x, right? So just like all before, what you are asking yourself is e to the power of what gives you x, right? It is important to be comfortable with ln because it is by far the most common form that you actually see logs in. No one okay, that's a lie. Engineers do it because they're weird, but no one really uses log to the base of anything other than e in most contexts, right? Ln of x, ln is by far the most common thing that you use, right? The key idea to point out is that ln and e are opposites, right? So if you take ln of e to the 2x, you will get 2x, right? And that makes sense because you're saying, what power do I need to raise e to get e to the power of 2x? I need to do e to the power of what to get e to the power of 2x? Well, obviously the answer to that is 2x, right? So this is the most important thing to get used to. The common form that you find this in is that you have some exponentials or indeed some logs, but usually some exponentials in your equation. And what you do is you get the exponential on its own on one side, and then you take logs. Because at that point, the other convenient side of that is that you can then apply log rules to everything else that you've taken logs of. So yeah, but yeah, this is an important thing to get used to doing, is the idea that natural log, ln and e cancel each other out. And equally, e to the power of ln of 2x is also equal to 2x. Right? They cancel each other out both ways.
Okay.
Other than that, I don't know. What about ln makes it confusing to you in questions? Which part of it do you get stuck on? I don't know. Maybe this would be better left to another time. I don't know.
Yeah, I think I need to find like specific question to ask because
Yeah. All right. Yes. Okay. Cool. I might suggest to Tom that, because I'm doing a lot of these, but I haven't actually done any like coming down and going through questions with you guys this term. So I might suggest to Tom that it would be helpful to do a kind of going through questions that you guys want to from a whole variety of papers, that kind of a sort of revision, supervision type thing at some point. I think that might be helpful to some of you, so that you can talk about questions on specific topics that you want to have a look at. So yeah, maybe. If you guys are interested in that, maybe suggest it to Tom. If you're not, then don't worry. Okay. All right. Yeah. All right. We will move on from there. We will briefly talk about trigonometry, and then we will take a 5-minute break or so at 5. So, trigonometry. You are presumably perfectly comfortable with tan is sine over cos and all of this business. It's worth pointing out, sometimes people, I particularly, I never remember these identities. They're a pain. It is definitely worth pointing out that these are just this identity at the top divided through by either sine squared or cos squared, right? So yeah, you don't need to remember these if you don't want to. You can just divide this through by sine or cos respectively. That is definitely something that is worth pointing out. These are your various graphs. I was looking through this earlier. I felt that it was the one thing that was worth pointing out. At your 0 lines for sine and cos, right? The green lines that are drawn here. What values are cosec and sec going to go to?
Infinity.
Yeah. So it's not very clearly drawn on here, especially here. It looks like it's kind of intersecting the line. Yeah, they go to infinity, cosec and sec. That is an important point to remember. Yeah, definitely the most important things to be comfortable with are this bit and again, actually, I don't know about for your syllabus. This bit by far, especially the cos one, is very, very important to be used to and have on the top of your head. Even if it's given to you, I don't know whether it is. It's very important and very useful to have these forms just kind of there and ready off the top of your head, right? Because you need to use them all the time for integration questions later on. So these are by far the most important. I don't know that you actually use the R and the displacement that often in this syllabus. Do you?
You do come across it, like.
You do? Okay, right. Fair enough. It was like every paper on the A levels I took, but yeah. Okay, so yeah, it's it's kind of difficult to talk about trigonometry too much in this particular context, because by and large, almost beyond any of the other topics, trigonometry boils down to the A-level trigonometry boils down to, here is a series of things that you need to know. I would say the most important piece of advice I can give you is actually go to your data booklets and make sure you know exactly what is given to you and what isn't given to you, and that you have learned what isn't given to you. That is definitely the most important thing you can do for trigonometry. I don't know how much of this is given to you or not, but it's all reasonably important to know. So yeah. All right. Is there anything more to say here particularly? I honestly don't think there is that much more to say, unless anyone has anything they want to ask about it.
No.
Yeah, sorry, this is one of those frustrating topics that is just a large amount of learning. Oh yes, and we've got our little odd triangular rules as well. I think you did those at AS though, so yeah. Okay, all right. In that case, why don't we take a 5-minute break for a minute, assuming you guys want to, and when you come back, give me a shout, tell me that you're here, and we will carry on then. Does that seem all right?
Yep.
Okay, I will see you back here in a moment.
Hello.
Hello.
Okay, right. There we go. We have everyone?
Yeah.
Yep. Okay. Right. Let's carry on then. So, our new topic for the next 25 minutes or so is differentiation. So, once again, this is... Okay, actually, right. If you guys don't mind, I would like to ask you a few questions about like the format of this and what we're doing. I want to make sure that this is actually being useful to you and that it's helpful to you guys and so on. Because I'm worried at the moment that that it hasn't been as useful to you guys as it could have been lately. I don't know how you lot feel about that. The plan from Tom had been to essentially be going through all of the topics on here each time we went through it. That said, I worry that means that for a lot of you, we're spending a lot of time just telling you stuff that you already know, and it's not very engaging and it's not very useful. Would you guys? Do you like it that way? Is that fine, or would you rather that I was, would you rather that I was asking you to come, asking you what specific bits do you want me to go through in a lot more detail that one of you perhaps doesn't necessarily understand, and are the others happy to kind of go through that and take it in turns to focus on parts that are perhaps more challenging for some of you?
Well, for me, I think that I'll be fine either way. There's always topics I need more help on than others, but I mean, if we skip the topics everybody agrees is kind of useless, then I don't think it would be bad going the way that we are currently.
Okay. What about the other two of you?
What exactly would the other?
Pardon?
Hello?
Hello? Pardon?
What exactly would the other option be?
Well, basically, the other option would be, for me to ask, would be for me to be asking, what type of differentiation for any one of you have you had problems in? Have you not been able to do, not understood in a past paper you've attempted or anything like that? And to focus in on, potentially just that one person who has been having trouble with it. Like we were talking about earlier, when I said, okay, perhaps this isn't the time to delve into the difficulties with logs with Kaneko, because it's a sort of group session and stuff. But I'm worrying that perhaps I'm doing Kaneko, for instance, a disservice there, and that this might be that. Yeah. So
I like the sound of that, as long as it's like obviously not completely useless for the other two. But I feel like that sounds like a good way to go about it instead of doing everything.
putting it the other way. Sorry, we'll run a little bit late maybe to catch up if this takes it. But putting this another way, just trying to get feedback off you guys. How have you been feeling about these sessions, and particularly any that you've had with me lately? Have they seem useful, or have you been coming away from them feeling, oh, I wish I'd done this differently or that differently?
I think like with maths, it's a bit different than to the other subjects.
Yeah.
It's just like with the other subjects, I find like you can go through the syllabus and ask questions and talk about stuff and get more knowledge out of it. But with the maths, I find it a lot harder if we're not applying it to a question.
Yeah,
I
I definitely think that it works less well with maths this way, doesn't it?
Yeah.
And I'm just not sure about like if I could apply it, even though like I might understand what you're saying. If then it would be the same if I was confronted with like a question.
Yeah, maybe if you, particularly if you all feel that way, maybe it would be worth moving away from this for the maths and back towards more of a focus on the papers, because that certainly worked okay. The trouble of it is it's trying to balance it between making sure that someone coming in doesn't just get thrown a paper with no idea how to do any of it. Because towards the start of last term, I was coming across several topics with you guys that, you know, you've been trying to do an exam question. I'm like, do you know any of this? And you're like, I've never heard of it before. I'm like, well, clearly something needs to change here then. So, yeah, that's interesting. Okay. All right. Well, we'll stick with this for the rest of today, and we will maybe try and look at changing things later on. So yeah, I apologize, but bear with me. Okay, so differentiation then. You're all fairly happy with the basics of it. Usually, and I'm assuming that you are all reasonably comfortable with these rules, right? Your chain rule, your product rule, your quotient rule. Yes? Usually in A-level differentiation, what people have difficulty with is the parametric equations and parametric differentiation and implicit differentiation, right? That tends to be where people struggle. Does that seem reasonable to you guys to focus on that? Or are there any of you that have had difficulty with the chain product quotient rules?
No, I think I'm good with them at least.
So going on from that then, which one of those two do any of you want to focus on particularly? Is one of them fine and the other one difficult, or are they about the same? Where are we setting out with these?
For me, parametric equations is pretty fine.
Yeah.
I don't know about the other two.
I think, yeah, me too as well.
Niels?
I think I'm fine with parametric. I'm not 100% sure. Implicit, I'm a bit less.
That tends to be the case. So parametric, let's talk about it briefly then. Because, parametric, provided that you understand what it is you're supposed to be doing, what you do is ultimately very simple, right? In parametric, you are given y as some function of t. You are given x as some other function of t, right? And you find dy by dx literally just by doing this, right? And if you struggle to remember it, you can always re-remember it by doing cancelling out of fractions, right? You've got dy. Why is this not? Dy by dt, dt by dx, right? So you're just cancelling the dt's, and this is just dx by dt flipped upside down, right? So yeah, you divide these into the other one, you get dy by dt. You get dy by dx typically as a function of t. The only other thing that is worth pointing out to be aware of is you can also, from this, right, this is no different to your normal y as a function of x stuff, right? You can find y as a function of x, and the way that you do that is you rearrange your x equation to get you rearrange it to get t equals some other function of x, right? You get t as some function of x, and then you substitute that into your equation for y of t, and you will get y as a function of x, right? So it works fairly nicely overall, and yeah, it ultimately boils down to just doing lots of normal differentiation, except with t's instead of x's. So generally speaking, people find that fairly fine. Implicit differentiation, a lot less so. We talked a fair bit about it last time, and we're probably going to talk about it again. So, the first thing to remember, implicit functions. These represent circles or lines with circular curves on a Cartesian plane. Okay, so yes, kind of, right? This is true insofar as you need an implicit function to represent that sort of thing. Okay? But I would always make the point that implicit differentiation is fundamentally no different to ordinary differentiation. Okay? Now I could. I'll just stick with here. So, if you normally have something like y equals x squared, you differentiate both sides with respect to x, right? So usually we talk about, oh, okay, now so dy by dx is, and you differentiate this. But you can also think of this in the manner of, well, okay, I just differentiate the whole equation with respect to x, right?
Yeah.
If you differentiate y with respect to x, you get dy by dx. If you differentiate x squared with respect to x, you get 2x. Okay?
Yeah.
And implicit differentiation is just applying this along with your chain rule to any slightly more complicated equation. A simple, nice one to look at is something like y squared plus x squared equals 1. What is this the equation of? What graph is that the equation of? Can you hear me?
Yes.
All right, okay. Does anyone know what that is the equation of?
No.
If you don't, it's fine to say we don't know, and then we can move on. But otherwise, I'm just sort of sitting here.
We don't know.
Okay, cool. Does that apply to everyone? Okay, I don't know. I haven't heard from the rest of you, but fair enough. Okay, this is the equation of the unit circle, right? This is a circle. This is x squared plus y squared equals 1. This is just a circle of radius 1. Okay, that's all it is. It's a circle around the origin of radius 1. Now, okay, so I thought you might know what that was, but fair enough, you didn't. Yeah, worth remembering that anything where you've got this kind of idea is a circular equation. So this is a circle, and we are going to differentiate it. And so just like before, we're going to go through and differentiate everything in the equation. And I'm actually going to do this from right to left because it's easier. So if I differentiate 1 with respect to x, what do I get? Kaneko.
Is it just 1?
Is it? Differentiate 1. What do we get when we differentiate just a number that doesn't have any x in it?
0.
Okay, so if you differentiate a number, just a constant number on its own,
Okay.
you get 0.
Okay.
Okay.
Mhm.
Yeah, that is definite. That's something that you need to be aware of. If you weren't before, then now you are. So hopefully that's all fine. So yeah, differentiating just a number gives us 0. If we differentiate x squared with respect to x, what are we going to get?
1 over 3 x.
No. It's 2x. Yeah?
Oh yeah,
When you differentiate, you bring the power down. Yeah, you kind of mixed up differentiation and integration there. Yeah. Personally, I would argue, just because people tend to be more familiar with it and it's simpler, the best way to avoid mixing up differentiation and integration is actually to just very firmly know what you're doing, because it tends to only happen with, or mainly only happen with polynomials and stuff. The best way to make sure that you don't mix up differentiation and integration is to learn one of them very firmly. And then if you aren't sure, ask yourself, how would I differentiate this? And then kind of do the opposite of that. So yeah, practice one more than the, practicing one is the best way to avoid getting mixed up, because if you know what one is, then you know whether it's that or the other thing. Whereas when you're kind of half knowing each of them, then that's when you tend to start to mix them up. Okay, now, the more interesting bit is differentiating y squared. Right, so this is where, okay, how do we look at this? Okay, this is where we are using our chain rule, right? The most common way that you come across a chain rule is something like, if you differentiate f of x squared, let's pretend that looks like a squared, you are going to get 2x times f prime of x squared, right? Where f prime is just f differentiated, whatever f is. It might be a log, it might just be, cubed. It could be whatever we want, really. So yeah, this is the way you're used to doing the chain rule, right? In this case, our outer function is squared, and our inner function is y, right? And so in this case, when we differentiate our outer function, and so apparently, never mind. Here, differentiating the outer function is just differentiating squared, right? So differentiating squared, we just get 2y. And then we multiply by differentiating the inner function. But the inner function here is just y. And what do we get? Shit. Threw my pen at myself there. What do we get when we differentiate y with respect to x?
dy over dx.
Yeah. Okay. Lots of the time, people learn this as you just differentiate everything, and then if it's a y, you multiply it by dy by dx. I think it is worth understanding what it is you're actually doing, why you're doing what you're doing, right? But this is essentially all there is to it for implicit differentiation, right? You differentiate every term in the equation. Then all you need to do to find dy by dx is just rearrange your equation to make dy by dx the subject, right? You've been doing that sort of thing since GCSE. So in this case, it's going to be minus x over y, right? That's all you're doing there. The kind of, how do you put it? The reason I think partly that people tend to find implicit differentiation hard is that actually the questions that they ask on it, they tend to use implicit differentiation as a kind of summative question for all of this, right? So it often involves lots of doing product rules, quotient rules, chain rules, and all the rest of it. So frequently they might have something like, you know, differentiate x squared y, right? So then you have to do your product rule on top of this, right? So you're going to get 2x y plus x squared dy by dx. Okay, this is just ceasing to write properly. What? Okay, right. Someone is messaging me on Slack to tell me to ignore them. That's slightly curious, but fair enough. Right. Sure, will do, buddy. Okay, so yeah. Yeah, okay. What do we want to say about this anymore? You've all said that you struggle with implicit differentiation, right? As we were mentioning, this tends to be, much like any other maths, is easier to go more in depth into with examples and stuff. Mm-hmm. So in the sort of, not quite there, but in the vein of that, what have you guys found difficult about implicit differentiation? What have you had trouble doing in the past?
For me, mostly it's just, I think, the combination of like all the things that is in there. So, and remembering then to like be aware of them and like add in, not forgetting anything small. Yeah.
So yeah, that ultimately comes with practice more than anything. As I say, yeah, there are the only suggestion that I can make about that is to develop you will without realizing it have already probably developed this on your own. So kind of formalizing it more than anything, but to develop an order for yourself that you do things in, right? So for implicit differentiation, where there is a whole series of different things going on, right? You've got product rules, quotient rules, chain rules, all the business going on in this. Develop a rule or a kind of list for yourself of what you do first, right? And then you can go through term by term and do each step one by one until you've done everything, if that makes sense, right? And then you make sure that you don't miss out, so probably, one of the best ways to do it is do your product rules or quotient rules first. So split your terms up as much as you can and just kind of write it down as I am differentiating this chunk and differentiating this chunk. So in the case of the above, just separate it out into, and I'm just going to use D so it doesn't take me forever to write, but D x squared y plus x squared dy. right? So just doing your product rule there. And then come back through and do the next step, and come back through and do the next step, and so on like that, right? So if you do have trouble with that sort of thing, and indeed, if you're struggling with implicit differentiation just because there's a lot going on for any of you, that can be helpful. It can also be annoying, but it can be helpful if it's becoming a problem. Either of the other two. Anything else that springs to mind about implicit differentiation that you would like to ask?
For now, I don't have it because for like specific question, I got some like question, but like for now, I don't have it.
Okay. Niels?
I'm not sure. I mean, thinking of questions on the spot just like this is not where my forte particularly.
Yeah, no, so I don't really mean questions insofar as, I did, this formula and I couldn't differentiate it because why? I kind of mean if there's anything general about it that you don't understand. I think it's unlikely because, as we've said, actually both of these, when you put it conceptually, they are quite simple to understand.
Yeah.
It tends to be the fact that they put everything together at once. So yeah. All right. In that case, we will move on to the last topics that we're going through, which is the first part of integration. So, a few things to point out here. Most of these you are reasonably happy with. Okay? For all of these, yeah. So for all of these that you are given here, these all follow the rule that integration is nice and simply the opposite of differentiation. Okay?
Mm-hmm.
And so they follow the rule, and they follow also the chain rule, if you look at it that way, right?
Mm-hmm.
In the chain rule, you have a function of some stuff inside, and you differentiate the outside function, and then you multiply it by differentiating the inside function, right?
Yeah.
You're used to doing. If you look at these, you are essentially doing the same thing here, right? Except you're doing the opposite, which is nice and convenient. So if you're integrating cos, for example, you integrate your cos, that gives you a sine, right? But then instead of multiplying by the differential of the inside, you are dividing by the differential of the inside. So in this case, if you differentiate the inside, you get just a, right? Ax differentiates to a, b differentiates to 0. And so we're dividing by a. Similarly, over here, we're dividing by a. In fact, all of these you're dividing by a just because that's how they've written them, if that makes sense. So that is the only real extension here to point out, is the idea of slightly extending the chain rule to the point of making use of it in this context to divide by the derivative rather than multiplying by it. One other thing that it is worth pointing out. So here we have 1 over ax plus b, and we have integrated that to log of ax plus b and divided by a, because ax plus b differentiates to a. If we have 1 over ax squared plus c, can we do the same sort of thing here?
Sorry, what did you say?
Okay, so the important point to remember with this extension is it only works if your inside function is linear. Okay? So it only works if your inside function only goes up to x. It doesn't work if your inside function has an x squared or anything more than that in it. Okay? The reason for that is that at that point you start to divide by like 2ax, at which point if you were to differentiate it, you then get product rules coming in. And so it basically what it means is that doing the opposite of differentiation is no longer as simple as just doing a division. Okay? So yeah, the important thing to remember about this is that it only works with linear pieces on the inside. What's important about this is that it means that if you have a fraction, you can only integrate it if it's got linear denominators. If you have something that has a non-linear denominator, you can split it up into linear denominators using partial fractions. Okay? And that is where most of the time your partial fractions actually show up, is integrating using partial fractions in some way. So yeah. All right. Not too much more to say about that without examples particularly. This one is more necessary to talk about. And in general, it is harder and more complicated to do. So integration by substitution. Integration by substitution. It's tricky and it doesn't actually come up all that often, but I would say most of the time it is what people find hardest in these sorts of courses. Okay? Integration by substitution is there by and large for when you can't do your integration by other means. Okay? And the idea is to make it into something simpler. The example that they've given us by here, we have y equals, so we have a function that is sine cubed of 2x, cos cubed of 2x, right? And they want us to use the substitution u equals sine of 2x. Oh, that's interesting. Is it exactly? No, it's not quite exactly the same blue. You can see it, but it's almost exactly the same shade of blue as my pen. Okay, I'm getting sidetracked. Squirrel. So if we, so I'm going to work through this up here as an example of what we're doing, right? So we're going to say that u is equal to sine of 2x. Okay? The first thing that you need to do when you are given a substitution, the other thing that is worth pointing out, unless I am very much mistaken, correct me if I'm wrong, you are always given the substitution to use if you do integration by substitution. Is that right?
Not always.
Not always. Okay, fair enough. So it is worth pointing out then, if you are trying to come up with a substitution, generally speaking, just it's not always a terrible idea to just use whatever the complicated chunk of your equation is as your substitution. Sometimes it would not be unreasonable to just use your substitution as like sine cubed of 2x, cos cubed of 2x. It's a bit of a weird idea, but it does work, believe it or not. Choosing your substitution can be a little bit more of an art than a science. That one, more than anything, comes with experience and practice. once you have chosen some substitution, the other thing to point out, if you are having to choose a substitution, usually it's relatively obvious roughly what sort of thing you should go for. If it isn't, try the first thing that you think of. Usually making some substitution that looks like what you have in your integral will make it doable. So just try it. Don't be afraid to just go for it and then try again if it doesn't work. The next most important thing to do is differentiate your substitution, right? So we get du by dx is equal to, and in this case, what's the answer? Kaneko. Du by dx.
Is it the need to do like?
Okay, so what have we got here? We've got a function with something inside it. Yeah?
Mm-hmm.
So the first step is differentiate the outer function.
Mm-hmm.
So if we differentiate sine, what do we get?
Minus cos. Cos.
There we go. Thank you, Grace. It's almost like I've got ears. Sorry, I'm being mean. Okay, so yeah, let's pretend that looks like a 2 and I'm not, completely terrible at writing. So differentiate the outer, we get cos of 2x. And then we multiply by differentiating the inside. So what do we get if we differentiate the inside?
That's right, just 2.
So we get just 2. Yeah. So we get 2 cos of 2x. All right. Now we have du by dx. There are 2 ways to look at this. You can either use this equation here, right? Or you can actually rearrange this to just make dx the subject in this case. So the other thing that you can do here is rearrange this and put dx up on one side and say dx equals du over 2 cos of 2x. Okay. Yeah, they've made this a pain. They could have used a much nicer substitution, but I guess that's just life. Okay, so we have now dx in terms of du, right? So if we substitute this in, well, we're going to get sine. Why is it? Oh god, it's making it really hard to write. We're going to get sine cubed of 2x times cos cubed of 2x times du over 2 cos of 2x, right? So first things first, this is going to cancel with this, and that's going to become a squared.
Yep.
Okay? Now, we know we can turn sine of x, or rather sine of 2x, into u's, right? Can we turn cos of x into u's very easily with that? Not particularly. So, but what we can do is we can turn cos squared into sine squared quite nicely, right? We know that cos squared plus sine squared is 1. So this is just 1 minus sine squared, right?
Yeah.
And so at that point, what we have, if we go down, is we have a half, and I'm going to use u just because it's shorter to write now. We have a half times u cubed minus u to the power of 5 du. Right? Because this is 1 minus sine squared, so we get sine cubed minus sine to the power of 5. But our sine is just u. And so in place of that, we put u.
Oh, yeah.
Now, this integration you can do very easily, right? That's a really basic polynomial integration. That becomes u to the 4 over 4. That becomes u to the 6 over 6. Nice and simple, I hope. And then, at the end, once you've got your integral and you've done it, well, then you can just substitute back in sine of 2x instead of your u. Okay? That one, yeah, so that's a decent example. And that is, by and large, just your method, right? This bit is probably the most important step in it, of recognizing what you need to do to convert the actual differential part. The only other thing that people tend to find tricky, or that is very tricky, is working out what substitution to use if you need to. That, more than anything, for now, is just going to have to be left to practice.
Okay.
Okay. Last 10 minutes, we are going to talk briefly about integrating our f prime over f. Grace, since I think you were in the last one, we went over this a fair bit then. The other two of you, do you recognize what we're talking about here, and are you comfortable with the concept? Yeah?
Yeah.
So is it actually worth our time talking about integrating f prime over f?
No, I don't think so.
Niels?
No, I think I'm good as well.
All right. In that case, what would you guys like to talk about? Because that is the last topic on our list for today. We have 10 minutes left, so we can talk more about bits of integration, if there is anything more about integration you would like to talk about, or anything else that we've gone over that you would like to go back to and spend some more time going through and looking at in more depth.
Can we go back to the example question? Because
Can we go back to the, sorry.
the u substitution example question?
Oh, yeah, yeah.
I kind of mix like integral and like differentiation again.
Okay, right. Let us, okay, give me a second. What we're going to do is I'm going to stop recording here. And, right. Okay, you should now be seeing Microsoft Paint in all its glory.
Yeah.
It would have been a tragedy if they'd actually removed this, wouldn't it? Okay, so I'm using Microsoft Paint because I can actually write perfectly fluently in this as opposed to the PDF editor. So our example is we are integrating sine cubed of 2x cos cubed of 2x dx.
Yeah.
Okay. And the question in this particular case tells us that we are going to use u equals sine of 2x.
Yeah.
Lovely. So the first thing we need to do once we have a u substitution. Now it's worth pointing out that in this case, if you were asked pick a substitution, right? There are I would say 4 feasible answers that you could use, right? And any one of them would ultimately work. You could pick sine cubed of 2x, right? And do the whole thing, the whole chunk, rather than just the sine of 2x. Okay? Or equally, you could do cos of 2x or cos cubed of 2x, right? It doesn't matter which of the two you pick.
Yeah.
Any of those will work. So it is worth realizing, because I think one of the things that holds people back most doing integration by substitution, I know it was when I did it, was being unsure about whether you're using the right substitution.
Okay.
And it's important to realize that the right there can sometimes be a right substitution, right? But in general, that just means that it's the one that makes the answer shortest. Most substitutions that are decent will still get you there. Okay? Not all, some substitutions are objectively wrong, right? You could use, u equals e to the x here.
Yeah.
Okay? That is a substitution. You can do it. It's going to make your life even harder, not easier, though, right? So that's a stupid substitution to make. I would hope that none of you would look at that and go, oh, I should substitute u equals e to the x in. That would be an odd thing to think, I feel. So yeah, the only general rule is pick something relatively, meaningful, like a cos or a sine or something like that, that is in your integrand.
Yeah.
So yeah. So next point that we make, we differentiate our substitution, right? So we do du by dx. So we differentiate over here, right? And we are differentiating with our chain rule. So we differentiate the outside, we get cos of 2x. We multiply by differentiating the inside, so we get 2. 2 cos 2x.
Yeah.
And then we can rearrange this because we want to substitute dx with du, right? So we rearrange this, we just multiply up dx, divide down 2 cos 2x, and we get du over 2 cos of 2x, 2 cos, equals dx.
Yeah.
And so we substitute that in, first things first. And so now we have the integral of sine cubed of 2x, cos cubed of 2x, du over 2 cos square, 2 cos of 2x is our new integral, right?
Yep.
Lovely. Now, cos cubed over cos is just cos squared,
Yeah.
right? And we have a half. So if I do this, we can now put in a half and we can turn this into a squared. Now, over here, we can say that cos squared of 2x is equal to 1 minus sine squared of 2x.
Yep.
Are we're all happy with this, right? This is our nice identity.
Yeah.
And so what we get now is the integral of a half sine cubed, and I'm going to stop writing the 2x's for now just to make life simpler. 1 minus sine squared du. And now we can multiply through the bracket. We get the integral of a half sine cubed of 2x minus sine to the 5 of 2x du. Now it's worth doing our other substitution, which is u is sine of 2x, right? You can do this substitution at any point. You just want to basically turn everything into u's. And we know that sine is just u, so we get the integral of a half times u to the power of 3 minus u to the power of 5 du. Last thing, we just need to integrate this. So I think, if I was hearing you right, Kaneko, that this is where you got mixed up again.
Yeah.
Was it?
Yeah.
So we are now integrating polynomials, right? So we have the half out the front still. if we integrate u to the power of 3, how do we do that?
This is just add 1. So
Yeah, so you up the power by 1, you get u to the power of 4.
Yeah.
And then what do you do?
And then divide by 4. Because
and you divide by the new power.
Mhm.
So divide by 4. And then, so what's the other one going to be?
U power of 6 over 6.
Yeah. Nice. And there we go. Lovely. So, yeah. You can try and remember a formula if you want it, but I think just kind of remembering it in words is a lot easier. So, yeah. Raise the power by 1, divide by the new power, whereas for differentiation, you lower the power by 1 and times by the old power. So, yeah. All right. Okay, I think that was a fairly nice example to work through. Hopefully that was okay. So, if there is nothing else to ask particularly, then we will probably stop there. Does that seem okay?
Yeah.
Yep.
All right then. I will see you guys, or some of you at least, tomorrow, I think. Grace and Kaneko, are you both doing chemistry tomorrow?
Yes, I do.
Okay, cool. All right. I will see you guys then.
Yep.
Bye-bye.